So I always want to have a go at. I've taken it from the textbook, work problem number 4, so I'm doing nothing that's not in the textbook, and they actually go through this, but they will do it probably slightly differently. So if you found this particular work problem under the section on differential equations, probably around about page 584, depending on the edition you've got, you could have a look at that. But let's do it together now as a group, and we'll see. You can compare afterwards. So what we need to do first of all is just play around with this thing algebraically and then see if we can separate variables. So we need to use a little bit of algebra on this to start off with. So we've got some initial conditions given theta equals 2 when t equals 1, so we should be able to come up with a particular solution for this. So we start off by writing 2t, t minus d theta by dt equals 5. Well, it's a differential equation. It's an equation because it's got an equal sign in it and it's got a differential in it. We've only got one independent variable, and it's t, and the dependent variable theta. So we're going to end up with theta equals something to do with t. Let's just play around with it first of all. So let's multiply out those brackets. So 2t times t gives us 2t squared minus 2t d theta by dt equals 5. Now what I'm going to do is try and get everything over the right hand side apart from the differential. So I'm going to use a few tricks. This is negative, look. So do you remember when we were talking about algebra ages ago? If the term involving the thing I'm trying to get on its own, which is this, is negative, effectively add it to both sides and it becomes positive. So the first thing I'm going to do is to this to make it positive, that term involving the differential. Now I'm going to subtract 5 from both sides. And finally I'm going to divide by 2t and write it with d theta by dt on the left hand side. So that's going to equal 2t squared minus 5 all over 2t. So looking at this one, we're in luck in a way. If we look at the original problem, theta, which is the dependent variable, only occurs once inside the differential. So really all we've got to do is to get that differential on its own, and then all the other terms are just going to be involving the independent variable t. So I'm going to end up with a situation where I've got the differential on one side, so all I need to do to get rid of that is integrate it, and I'll end up with theta. So that's going to be really easy because I'm going to end up straight away with the explicit solution. All I need to do now is take the dt over here and integrate both sides. So that I don't need to separate variables, I don't need to play around with getting y's on one side and x's on the other. I've just got to get all the t's on the right hand side effectively to separate them. So I can say that the integral d theta equals the integral of 2t squared minus 5 over 2t dt. So I've got an integral to do on the right hand side. The integral of effectively 1 d theta is just theta. So the left hand side is theta. Now we have to integrate the right hand side. We might be tempted to think about things like substitution and all those sorts of things, but actually because I've got just one term on the bottom, 2t, I can separate out this into two fractions and call it the integral of 2t squared over 2t minus 5 over 2t dt. So So I can separate out those two fractions. So again, it all comes down to the algebra in these things. I can simplify this integral like that. I can do a bit of cancelling now. T's cancel, top and bottom, and the 2's cancel. So theta equals the integral of t over, just t rather, minus 5 over 2t dt. So it's getting simpler and simpler all the time using algebra. Now this right hand side is straightforward, isn't it? I just integrate each one separately. Whoops. So I integrate the t and I integrate the 5 over 2t, and those we're familiar with. We can write down the solution to those two. So write down the integral of the right hand side, and that will be our explicit solution, not forgetting the c. So hopefully if you've done this you ended up with that, and that's our explicit solution. We don't need to do any playing with it, it's automatically in terms of theta. So that's fine, we've got our general solution. This is the general solution. It's the general solution because we don't know c. So we've got our general solution, we now need to get the particular solution. So we go back to the original problem and look for our initial conditions, which are theta equals 2 when t equals 1. So we put those values for theta and t into the general solution. So we go back to our general solution and say theta equals 2 when t equals 1. So we put them in. 2 equals 1 squared over 2, which is 1 over 2, minus 5 over 2 log 1 plus c. And then we work out what c is from there. So I'll just pause this while you do that little sum and work out what c is. So hopefully you did something like this. You bring the half and this over here so we can get c equals this, and we get answer 3 over 2. If you use a calculator, looking at it again, could you have done it without the calculator? Thinking about the logarithm. What does the logarithm mean? The natural logarithm means what power do I have to raise e to get 1? Answer 0. Everything to the power 0 is 1. So in fact this is 0. So actually it's just 2 take away a half, which is 1.5 or 3 over 2. Okay? But of course you get that anyway if you do it on the calculator. Okay, so there's our value for c, so we can now write down what the particular solution is. So therefore theta equals t squared over 2 minus 5 over 2 log t plus 3 over 2. And that's our particular solution. In other words, we can now use that to find the value for theta given any value of t, and we can plot this on autograph and see what it looks like. Of course, in any situation you can look at it and try and tidy it up algebraically. Not essential, but I would always do that. I could factorise that because a half is common to all of those, so I could take a half outside the bracket to leave me with that theta equals a half t squared minus 5 log t plus 3. I might or might not want to do that. And then we need to think about the range of values over which this thing will work. And so as soon as these things come in, we have to think, often one of the things we ask ourselves is, well, what happens if t equals 0? And we've already established that when t equals 0, the natural logarithm tends towards negative infinity. And so we're going to have a situation where if that's negative infinity, if I'm subtracting it, then that's going to be positive. So if t equals 0, this is gone. So we're going to have actually the thing probably shooting off to infinity when t equals 0. So we need to be careful about this model when t equals 0. And if I plot it on autograph, which I did earlier, here it is, and plotted the general solution, it looks like that. And so we can see problems start when it starts to approach 0. If I look at the constant controller again, what happens if I change the value of k? Let's increase the step size a bit. Oh, sorry, yes, see, what's going on here? So if we change the value of c in this, then that's actually going to change not the shape of the function, but the position of the function. So in other words, again, if I want to know, well, what's the value of the function when x equals 2, or t equals 2, I look across. Well, that's no good, because for the general solution, that could have any value. So I need to have the particular solution. In other words, I need to calculate what c is, and in this case, it turns out to be 3.5. So if I go back to autograph now and change that to 1.5, then I've got my particular solution, and now I can use this function to get values for theta.